It's my great pleasure to introduce our next speaker, Professor Bahman Gharesifard. Bahman is a professor at UCLA in the Department of Electrical and Computer Engineering. He's the recipient of mention in their entirety, but in particular, the SIAM Best Paper Prize from SIAM Journal of Control and Optimization. He is an Alexander von Humboldt Fellow, as well as a Best Paper Award from the Society of Information Theory. So he's going to talk about some of his work, actually joint work with me, on mathematical analysis of actor-critic methods. Thank you, Bahman.
Thank you, Alex. Thanks a lot for the invitation. I'm going to try to stay close to here. Yeah, this is going to be quite a different talk in that it's going to be a theory talk, and it's going to be very basic, really, really basic. So if you're in the audience, you've never seen reinforcement learning, this is for you. If you're in the audience, you know reinforcement learning, you should just leave, okay? Because it's pretty basic. As Alex mentioned, this joint work with Alex here at Boston, which we kind of did maybe around a year and a half ago, we started thinking about this. So as I said, I'm going to talk about basics of reinforcement learning. And the setup is a Markov decision process. It's been talked about quite a bit today. So finite number of states, and the classic version, right? Actions denoted by A, and you have a transition probability matrix, right? You're at state S, you take action S, you move to the next state, okay? Great. And you have expected cost that I've shown it here. And then this is the rough idea of objective of classical, basically, optimal control problems or reinforcement learning problems, is that you basically want to find a policy that minimizes basically a discounted cost, okay? And here, note that this CT is random, right? Because you have underlying MDP, okay? Great. Now, what is the basic part of reinforcement learning? That this state and action space is large. So we're going to parameterize our policies, right? Like we just imagine if the action space is too large, you're going to, if you're a control guy sitting in the audience, you do it all the time, for instance, linear policies, etc. So you're going to parameterize it by theta, and I'm going to use pi theta from now on to show the policies, okay? Now you're going to have a value, okay, associated to every state S, right? You have a value. And here, basically, your initial condition could even be, according to some distribution. So the value function from now on, I'm going to put it denoted by v theta, drop this eta. So this is the value function people have been talking about today the whole time, right? So that's the value function, okay? Precisely defined up here. Now, in reality, however, many times we're interested to keep track of not just the action, the state, but the state and the action. So to every pair S and A, okay, you want to associate some form of value. This is what's called the Q value, okay? And I've denoted it here. So this is basically the value when you take action A at state S, okay? And you follow the policy pi theta. Remember, the policy from now on is parameterized by theta. That's the power of reinforcement learning, right? Is that now you only have to deal with theta, which is potentially much smaller in size than the S, okay? Now, this v theta, there's just anybody that, doesn't know anything about anything even, right? When you know the MDP, you say, well, I have this value function. It's parameterized by theta. Great. This function, I want to basically, I compute this derivative, okay? Because if I have this derivative, then I can improve my policy. Because my policy now is really parameterized by theta. Updating it, meaning updating theta. So here is the classical theorem, right? Which is the policy gradient theorem, which is kind of quite a nice result, very easy to prove, telling you what the derivative of this v theta is with respect to theta. You can calculate it. When you look at this calculation, right, the parameters that show up, okay, one of them is this basically probability that the state is S at time t, if the policy is followed. And the other element that you see up there, if my cursor works, is this guy Q, okay? This Q guy, you need to know it, okay? You need to know the Q if you want to compute this derivative, okay? Because you want to do a gradient step towards it. But you don't have it, right? In the general setting, when you don't have the MDP, you don't have this guy. What you do, So as I mentioned, let me just finish this discussion that, the rough idea is very clear. We do what we do in basically setting of SGD, right? Because as you can see, you have, if you look at this derivative, it's actually a bunch of sums, right? But the whole idea of SGD is we're not going to do this big calculation, but we're going to sort of do a SGD version of it. You will see this in a second. And by that, I mean, as you can see this big sum, you're going to get rid of the sum, okay? And you're going to sample what's inside appropriately, right? It's like sum of bunch of functions. That's what SGD does for you, right? And you just have to sample it appropriately, proportionally, so that you have uniformly looking at this function in all directions. And this is what you're going to get. If you sample this appropriately, as I mentioned, okay, who cares with some probability, right? This probability is just adjusted so that that sum is going to give you the sum you need. This is the update you're going to get, right? As I mentioned, this is how you're going to update your parameters, okay? And as you can see, there's a learning rate here that I've called it beta t, okay? So that's how you update your policies. But the caveat is you need to know the Q. What do you do about that, right? Well, the policy gradient method often accomplishes this by doing a rollout. What's called a rollout. So you're going to roll out a bunch of trajectories, you're going to get an estimate of this Q function, and then you're going to step into this gradient direction with some learning rate, okay? Great. But the actor-critic method, which is going to be the discussion of this talk, okay, we're going to produce a separate estimate for this Q function. As I mentioned, it's just an intro to reinforcement learning if you've never seen it, okay? Now, here's what classically is done, right? This Q function, you don't know it. You're going to grab a bunch of really representative feature functions, call them phi. For instance, this could be, just think about this as like a Fourier series or something, or just think about it as Galerkin functions, some very representative functions. And you're going to say, well, let's say this Q function is a linear, basically sum of these with some coefficients omega I, and these omega i's, these weights, are what I'm going to find out, okay? So the only thing that I need to know now are, or update are basically these guys. And these feature functions, as I mentioned, they need to span everything, they need to be nice, etc. Let's put that aside, okay? So this is what you do, basically, okay? Now, I want to tell you a little bit further, like I want to kind of narrow down exactly how we go about doing this, okay? And in order to do that, I'm kind of following classical results of the Stiglitz and Van Roy, and let's just take a look at a sequence of state actions, okay, with the corresponding rewards, right? So, and I put out the actions. Let's just take the states, S0, S1, S2, so on, right? With the cost C0, C1, C2, okay? Now, suppose that you've estimated the value at ST to be VST. So you've done that. Suppose somehow you've estimated this value. Now what you can do is when you look at Bellman principle, okay, you say, hey, wait a minute, the value, okay, need to match this CT plus 1 plus gamma VST, just by Bellman principle, right? So now you tell yourself, well, if there's a mismatch, I need to see why there's this mismatch in my estimate, right? What you do with this information, you simply take your estimate of that value, the estimate you've done, and you're going to nudge yourself a little bit, right, into the direction of this difference, just to make your estimates of this value basic. This is written for value function. We're estimating the Q function, but okay, we know these two are kind of the same, right? I'm writing this for the value function. So that's really the principle of it. So the principle of this thing, which is going to be called temporal difference learning, it came up in one of the talks, right, on games. So this TD dynamics simply comes from Bellman principle, okay? Now, great. So let's go back to this idea. Rather than applying on the value function, let's apply it on the Q function. As I mentioned, it's the same principle, right? You generate some state action pair. This has to be according to a stationary, but let's not go there for now. And then you follow the MDP, okay? And what you do is you're going to exactly compute those two values that I mentioned, and I've written it up here, and use that to update those coefficients, simply, right? So remember, I gave you the policy gradient where you're updating the theta, okay? Now I'm giving you another update, which is going to update your Q function, okay? So this difference is exactly that difference that you just saw. I've marked it here with color so that you can see it. Great. Now this is what you got. You got actor-critic dynamics, okay? Now the learning rate here is a beta, okay? And the learning rate here is alpha, okay? And there's a projection that I've put in here, but that's not, don't worry about that at this point. So this is what's called the actor-critic dynamics, okay? Great. Now, this goes back to sort of, now the classic part is kind of done. Now let me tell you a little bit about what we know about this dynamics. First of all, note that this dynamics is pretty coupled, right? I think it's obvious that it's coupled because we saw the Q function there, right? And then you have to do the other one. Both depend on each other. Now, what do we know about this dynamics? Okay, classically, what do we know about it? So this is a very difficult dynamics to study in general, and let me tell you why. It's very clear, it should be very clear, because one of these dynamics is a SGD. Remember, one of them is a SGD. This one on top, this is a SGD. So one can say, well, you know, maybe I can do some SGD with some error, right? Some error that's coming from the critic sort of into the first dynamics. Maybe I can do something like that. Well, in order to do that, you basically have to do a timescale sort of business to be able to do that, right? But whereas the other direction that you need to argue, because you see the issue here so far, I've told you the first one is the SGD. The TD dynamics, we don't know what it is, right? We currently do not know what kind of dynamics it is, and that's what makes this thing a little challenging, okay? And so what I want to do, I want to dwell on talking about TD dynamics for the next 5 minutes, okay? Just to tell you what the TD dynamics actually does. So let's fix theta. Let's fix theta and just look at the omega update, okay? This is just the omega update. You can see it. I just renamed things here, okay? I just renamed it. I reformatted it in a way that if somebody knows dynamics or knows a little bit of control, make some sort of association to this because they're like, ah, look, this looks like a linear time varying system, right? With a bunch of stuff added to it, right? It's just linear time varying, right? With a bunch of added things, right? So one of the things that was shown in 1997 classical result was if you have this sort of stochastic approximation type sort of rates, alpha t, then this dynamic converges. This is classically known. So fixed theta, we know very well. This dynamic is going to converge. And in fact, for a fixed theta, anytime you see my talk omega with a subindex theta, it means it's the limit of this dynamics, okay, for a fixed theta. So this we know. The problem is when theta is changing also. Okay, the interconnection is where the problem is. Now, one of the things I want to tell you of why TD is not such a simple thing, even though it looks very simple and innocent, is that TD in general is not a gradient flow. Okay, if there's one thing you need to learn from this, it would be this, right? TD is really not a gradient flow because AT is not symmetric in the previous slide that I just showed. However, it is something that's close to a gradient flow, okay, to a gradient, and it's what's called the gradient splitting. I don't want to dwell on this so much, but this is something that actually Alex and his student in 2021, they sort of have a paper on this TD as a gradient splitting. Actually motivated me to start talking with Alex about this problem because I find this quite interesting, okay? What it says is that, this is the simplest form of it I could write, is that even for a quadratic function with AB symmetric, if you have a B that sort of splits this A, okay, and you define this function H, this function H has many of the good properties of the gradient, many of them. Some things that you care, right? Like a first order condition, et cetera. These things, much of it works for this guy, okay? And so it turns out that TD has this property, Okay? It's sort of a splitting of a gradient. It's not truly a gradient, but it's a splitting. So let's see where we are, guys. Okay? Let me give you a summary of where we are. We have a stochastic gradient flow, okay, coupled with another dynamics, which is not quite a gradient flow, and they're interconnected, okay? We have these rates alpha t and beta t, okay, which we want to control to see if this interconnection converges. We can give some convergence result on this, okay? Actually, we need more than convergence. We're going to go after convergence rate, okay? And so let me tell you a little bit about what is the path that's taken typically, okay? What's the path that's taken? The path that's taken is to use a 2-time scale approach, okay? So what you do is you're going to take the beta t, alpha t on different time scale. You're going to slow down the actor. You're going to slow down the actor, and then it becomes what I exactly told you. It becomes SGD with some error. And then you can pull out results from wherever, right? And you can just say it's going to work. So if you go on a 2-time scale, okay, this is the typical approach for convergence rates, et cetera, et cetera. Now, let me tell you, actually, when I started looking at this around 2021 with Alex, the best rate that was known for the 2-time scale was 1/t⁵, okay? If you want to write this in terms of sample complexity, this is roughly speaking the sample complexity, okay? Now, this is a little unsettling. Why? Because for SGD, you have 1/√t. So the question is, why is there a gap, right? That's the question. Why is there a gap? Should this be there? Is it because we're slowing down, or what is the reason, okay? So this is where we kind of started thinking about this. I mean, that's when we started thinking about this. So what our initial kind of idea was, we're going to go after a single time scale. And I think at the time, there was no result of single time scale, except a parallel result that came at the same time we were working on this. So let me tell you a little bit about the tedious part of this without really dwelling too much onto what goes in this. So as I mentioned, you know, anytime I fix the theta parameter as a subindex, so this A theta, I use it for the expectation of AT, B theta for expectation of BT, just a bunch of notations in here. What I want to tell you is, like, remember I mentioned to you that if you know anything about dynamics, guys, you should, when you take a look at this I plus alpha AT, you should think about the following, that if this A, okay, if I want this dynamics to converge, I need some property, okay, to hold. For instance, if this matrix here has, it's a spectrum, right, with size bigger than 1, then this is going to blow up, right? So I need to control the size of this guy. This is one of the things that is obvious from this dynamics, okay? And so what you do is, if you really think about it for 5 minutes, you realize that you're going to need a condition like this to bound this by a negative number, and then that allows for this to sort of converge, right? This is what you're going to ask, okay? Now, this property, okay, in this type of business, you can't just ask for a property. You need to see what that property means. Here's how you can, for instance, guarantee this property. So the first thing I want to tell you, as I said, I have to tell you some regularity. It's not that this dynamic is always going to converge, right? The first thing I'm going to ask you is, give me some uniform mixing, enough mixing. This policy you have has to visit everywhere, in a way, right? Roughly speaking. So this is the exploration, okay? I'm going to call it the exploration assumption. And now one of the things that's important for people who work on the sample complexity is this mu, its appearance is important, okay? In particular, I've made a note. We wish to obtain estimates that degrade not too poorly with the size of mu, okay? I think at the time we worked on this, the best bound was mu to the -4, okay? If you're in this line, I think, as I mentioned, you understand why this is important. Now, the second thing is the critic. As I mentioned here, I've put this approximation sort of sign, and I've never told you what it is. In the classical version of TD, okay, in statistically Van Roy, this is taken to be linear, okay? But nowadays, people use neural networks, for instance, in this portion, right? Which is not going to be linear, but the basically quality of it, we're going to measure by this delta. So there are two parameters you need to see in my estimate show up. One is mu, the mixing. The second one is this delta. How close is it to linear, roughly speaking? Okay? If, many of the estimates in the literature are anyway for delta equals 0. Great. Now, as I mentioned, as any other work on this topic, right? You typically need lots of properties, right? Which I will not get to sort of get to in details. For instance, you need Lipschitzness of critic update, right? You need some boundedness assumptions, right? Because even to sort of apply the results for the SGD, you need some Lipschitzness, regularity, et cetera, et cetera. It's not that we're going to assume these, okay? I did not list assumptions. A lot of them you can actually drive with very basic properties on the underlying MDP. I don't want to, it's afternoon, so I don't want to get to details of these, but if you're interested, you can look at the paper, see how we managed to prove all these properties. Okay. Now that we have everything in place, I hope you understand where I'm going. I have this interconnected dynamics, right? If I slow down, okay, one of them, I know what's going to happen. If I don't slow down the actor, right, I don't know what happens. And in this case, so I want to give you a reformulation of this actor-critic dynamics. And in order to do that, let's just literally take the errors that we're interested in. Remember, anytime I have an omega with a subindex theta, this is the limit. You fix the theta t, you take the limit. Okay? That's the limiting behavior, which we know it exists for TD. Okay? So I'm taking the difference. So this is the critic error. And I'm taking the actor error simply to be, how far it is. I mean, this is not convex, but basically how far is it from a stationary point. Okay? So these are the two errors I'm after. Okay? Any bound I'm going to give you going to be based on these two errors. Now, here is a very interesting reformulation. Well, I mean, we've already seen it. Is a reformulation of basically the omega dynamics, right? This is interesting because here, as you can see, I'm using this A theta and B theta, which are those expectations. As I mentioned to you, I'm using this notation nabla because sort of this is a gradient splitting. It's not quite a gradient, but it's a gradient splitting. So this nabla tilde is this guy, okay? So it turns out you can write the omega dynamics that I showed you in this fashion plus, okay, a random variable with 0 expectation condition on the path. So that's what I was trying to tell you. It's a gradient splitting plus some noisy part coming from, right? That's some noisy part, okay? So it's a noisy part so some noise kind of injected in here. And on the other end, I also mentioned to you that this is literally a true gradient, okay, with the learning rate beta, and similarly with the random variable with 0 conditional expectation. So these two noisy dynamics, they're kind of coupled, okay? I hope everybody understands what I'm saying. This is the reform. I'm just writing it the way I mentioned to you in words. I said one of them is a gradient, the other one is a gradient splitting. I'm just writing it down, okay? So far, so good, I hope. Now let's see what I can tell you, okay? I mean, the analysis of this is not easy, but I'm just going to show you what we can obtain, okay, on these two estimates, right? So here's the first result, okay, on the critic update. The interesting part to keep in mind is we're taking alpha t, beta t of the same rate. That's why it's single time scale. Okay? Unlike what's in the literature, we're choosing the same rate, both at 1/√t, give it a take, up to some constant. Okay? Now, here's the thing we can prove. Okay? You should think about this term as like the critic error. Okay? Right here, I mentioned to you the delta is going to show the error of the critic, and this is what you would measure as the error, right? The time average. And as you can see, this is a very mysterious looking inequality. The first time I kind of saw it, kind of looks a little mysterious because you have this term here, and then you have the square root of it here, plus the actor error showing up, okay? This is the part that is not quite something you've probably seen in the literature. Now, I have also tried to, mark these parameters mu, okay, which are the mixing parameters. I mean, the parameters look complicated, but I've tried to sort of mark them so that you can see it, okay? Now, the other side of things is a little easier because this is really SGD with error, okay? And so when you write it now, you get the opposite of that inequality with the actor error in this side and the critic error on this side. So you got these two inequalities based on these two analyses you've done. Now, the issue is, I think, right, is how am I going to put these two inequalities together, right? Like it's a little bit of, because of that, a square root is not sort of nice looking. And a nice way to look at it, and I want to now tell you, so you got these two based on sort of the analysis you did. And so here is, what's called the small gain theorem. You have seen it or you have not seen it. But, you have some sequences, X and Y, with some norm, okay? And if you look at this first equation, this first inequality, guys, right? You see that whatever norm it is on X, it's related to the square root of it plus a constant time this guy. Just like the first inequality we had, right? And the second one looks like the second inequality we had, okay? Typically this is, and remember this shows an interconnection between the X and the Z, right? A small gain theorem typically requests for the coefficients, right? Some coefficients behind basically these inequalities to be less than some value, here 1. So one of the things you can show, I mean, this anybody in the audience, even a high school student can show this. If this is less than 1, then you can get a bound on X. And that's what we exactly do. Because we have these two inequalities here. So what we're going to do, we're going to put that condition, okay, to be able to get what we need. One of the things I forgot to mention is take a look. This delta shows up here, okay, because I did not talk about this. The delta shows up here, okay? The mu shows up in the other inequality. You can see, and the delta is here also coupled in here, okay? But as you can see, the mu, it's very important for me to note that this mu, everywhere that you can see here, it's basically just 1 over mu. It's all that showed up here in my inequalities. Now, let me show you what happens when I basically pack these two things together, okay? So this is sort of the result we obtain. With the alpha t 1 over square root of t, beta t 1 over square root of t, give or take, you're going to get, constants have to be chosen appropriately because I put some conditions on the constants, which I didn't really go through so much. You can get basically a convergence rate of 1 over square root of t, okay, sample complexity of epsilon -2. And as you can see, mu shows up here with mu to the -1, as you saw already in my equations. And delta, we expect delta to show up anyways, right? Because if, and so this is sort of what we expected to see, right? The same rate that we would get for SGD, we're going to get it basically for basically actor-critic. I mean, as I mentioned, if you think about sample complexity, in terms of sample complexity, you're going to get basically mu to the -2, epsilon to the -2, which is, I think it still is the best bound available. I don't think this is improved. I might be wrong, Alex. No, I'm right. So this is still the best bound. These things you never know within the, the epsilon -2, of course, you cannot improve it, but this mu to the -2, you might be able to improve it because the best known was mu to the -4 before we worked on it. But it's very nice to see that you get exactly what the SGD sort of is providing, which is was hidden because of not using single time scale, in my opinion, right? Now, basically, the technique that's used here is the important part, in my opinion, right? Is because the technique that we've used, this coupling of a true gradient with a gradient splitting. I believe that this technique can be used to improve lots of existing bounds. We haven't done it, but I think you should if you're interested. One of the ones that is an interesting one, and I on top of my head, the best known bound for what's called natural actor-critic, where you have sort of underlying metric, is epsilon to the -3 sample complexity. And for instance, it would be very interesting to see if one can improve that convergence bound using these techniques that we develop here. This is the paper, just appeared in SciCon. And I also added this other paper that's we just posted this on arXiv. I thought it's a good chance to sort of display this because this took a lot of efforts, and I'm, one of the results that I'm quite excited about on linear quadratic regulators using a reinforcement learning lens. And so if there's any comment on this paper specifically, I appreciate if you let me or Alex know. I think it's a good point for me to stop. Thank you.
Thank you. Do we have any questions?
Hi, very good talk, thank you. This may be a sort of RL naive question, but a lot of the difficulty it seems like you're having is because the Q update was not a gradient. Would it have been better if you had instead just taken the gradient of the square of the difference between the reward plus next feature times W minus, or times omega minus current feature times omega, and then it would have been a gradient? So basically you have this, maybe if you go back to the slide, it'll be easier for me to.
I think I see where you're heading.
Yeah. So if on the far right, okay, yeah.
Right here?
Yeah, if you took the thing inside the parentheses and squared it and took the gradient of that, then the only difference would have been the thing on the far right.
So your point is take this difference.
And then square it.
Okay, square it.
And then I want to take the gradient of that. I want to make that difference 0.
So I think the thing that you're going to see there, and this is what I'm trying to think about, is that matrix A, T that you saw. You're basically saying use A plus A transpose in a way. Because as soon as I square this, right, roughly speaking, that's what I'm going to get. I'm trying to think, is it implementable, that A transpose? I think.
Yeah, it is, because the square, if you square it, right, the only thing that will change is the gradient that you'll get. The phi at the end will not be phi of S prime A prime, but phi of S prime A prime minus phi of S double prime A double prime.
I think that this is related to something called Bellman.
Yeah, squared Bellman error, yeah.
Minimization. And I would really have to go back to the paper from 1995. But I think that there's counterexample.
Yeah.
Would show that if you do Bellman residual minimization, this has some pathological biases.
Yeah, there's example. I do. Yeah. I have to, on top of my head, I don't have a quick answer, but I believe that it's not immediate to me why it should work. That's what I'm trying to think. Is right? Because this is built based on sort of Bellman principle, but what you're saying is a little bit of changing that dynamic. So I have to think about it. Alex, do you have anything?
Yeah, one comment is that people have tried this,
Sure.
and it somehow doesn't work well in practice.
Yeah.
And I don't have a good intuition for why that is the case.
Yeah.
Okay, thanks. Sorry, like I said, RL naive
it's
question.
a very good question. It's a very good question. Yes.
Oh, there's.
Maybe a quick follow-up on that is another reason I know is because of something called double sampling. It's if you have another file, if you allow to sample at this time t, another next state action pair, if you're allowed to do that, then there are some way to get around with that, but otherwise there are some bias appear in the aspect of that. So eventually you cannot show it to do the policy evaluation correctly.
Yeah.
In fact, in the linear function approximation case. Yeah, but anyway, so my question is more like maybe I missed something. It's great,
Yes.
very super interesting. So is this restricted to the ID sampling case? Because we know in RL, especially if you are doing actor-critic, everything is following a Markov chain. So that seems to be the key challenge
Yes.
in matter of analysis.
We wrote this for ID, but I believe that it's already extended to Markov. Yeah, it's already extended to Markov, I believe.
In this paper.
Not by us, however.
Not by us, not by
Oh, I
us,
see.
by some other group right
I
after
see.
the paper.
Using
Yes.
the same technique.
Same
Yep.
technique. It's not difficult to that,
I
do
see.
that extension.
I see.
I
So
believe.
another quick question is more like, let's say we go back to the tabular case.
Yeah.
Would this result give us like a global convergence in terms of the global optimality result
Yes.
instead of stationary point?
Yes.
So you can get it from the analysis
Yes.
directly? I see. That's also in the paper, or it's in the...
I don't know. Did we point out the tabular case? No, we didn't. We didn't point it out, but I believe it's doable.
I see. Yeah, I agree.
I don't know if somebody's written it, but I don't know. Yeah.
So the last question is more like for general audience, because for control people, we know what small gain theorem is, but maybe could you help us better understand the connection of
basically,
this
generally
small gain
speaking-
theorem and this analysis?
Yeah, so generally speaking, a small gain theorem, that's what it does for you. You have two dynamics, right? They're feeding to each other, right? And you want to know, even if both of them are stable, guys, take two dynamics that are stable, interconnect them. There's no reason the interconnection is going to stay stable unless what's called their gain, right, somehow, right, pairs up in a way that when they're interconnected, things are going to stay well. And a small gain basically tells you what should that be, right? What should basically the interconnection satisfy? So roughly speaking, I mean, in a 1 minute.
We may need like a block.
Yeah, you need a block
to
of
see the
basically
small
things
gain.
feeding to each other. Yes, and that's the case here because the two dynamics are feeding to each other.
See. Thank you very much.
Yes, thank you.
Okay, do we have more questions?
Quick one if I can. So, I mean, it's really great that you can avoid these really small step sizes, like vanishing step sizes. But just to get some intuition, you have these constraints on the constant C step size that you pick for the actor.
Yes, like
It-
here, you mean?
Some,
Yeah, I think I know what you mean. This C
Somewhere.
up, this C here.
yeah.
I think-
Is that still intuitively saying that the actor should be updated quite slowly? Is that the...
I mean, this is a constant. We can exactly characterize it based on the parameters. So even though it might be, let's say, large, right? It's still not at the same size as, like, it's still the same timescale as far as T is concerned. You know what I mean? You give me the parameter system, I give you a C, right? So in that
Get that.
sense, as far as little T is concerned, they're the same timescale.
Mhm. Yes.
But in the paper, we exactly write it in terms of parameters. We can obtain it exactly in terms of parameters, yes. Thank you. I actually should have displayed it, now that you mentioned.
Any more questions? Okay, let's thank the speaker again.